Welcome to my class 12 physics chapter that is alternating current, and today we will discuss about AC voltage applied to one capacitor. This one is the capacitor. Capacitor means here two parallel conductors are there. This one is the first conductor, this one is the second conductor, and this is the distance between the two conductors, and this distance is very small, so that is known as a parallel plate capacitor. When AC voltage is applied to this capacitor, then what happens? Clear? First we draw the circuit diagram. These are the external wires, and here a capacitor is connected. This one is the first plate, this one is the second plate, both are parallel to each other, and here AC voltage is applied. This one is the symbol of a AC voltage in a circuit, and these are the external wires. Now the circuit is closed, and capacity or capacitance of this capacitor we write C. Applied, this is the applied EMF. We write for applied EMF, that is E is equal to E0 sin omega t. Clear? And here applied EMF is alternating in nature. That means initially its value is 0, value is gradually increased, and here value is maximum, then value is gradually decreased, and at this point that is 0. That means this is the positive half. For positive half of the voltage or EMF, capacitor, this is the first plate of the capacitor. First plate of the capacitor is positive charge and second plate is negative charged. And during the negative half of the voltage, then first plate of the capacitor, first plate means we write, suppose that is plate A, second plate we write that is plate B. Then plate A now becomes negative charge for the negative half, and plate B becomes positive charge. And here applied EMF, that is given E is equal to E0 into sin omega t, and we will calculate the instantaneous value of current at any instant of time from this expression. Clear? And this one is the circuit diagram, and here only a capacitor is connected. Suppose its resistance is very small, and this circuit is also known as purely capacitive AC circuit. The circuit is known as a purely capacitive AC circuit because your alternating current or alternating EMF is applied. Clear? Then we derive the equation for instantaneous alternating current at any time t, and we know EMF E is equal to E0 sin omega t. That implies we know this relation in the chapter electric potential and capacitance. You know Q is equal to C multiplied by V. Q is the charge, C is the capacity or capacitance, V is the potential difference, and here in place of V, E is there, so that we write Q is equal to C multiplied by E. That implies E is equal to Q by C, so that in place of E, here we write Q by C, that is Q divided by C is equal to E0 sin omega t. That implies Q is equal to, we take C to the right hand side, that is C multiplied by E0 sin omega t. That implies we take derivative with respect to time in both sides, so that we write the left hand side becomes dq divided by dt is equal to d by dt of C E0 sin omega t. Clear? That implies what is dq by dt? You know the formula in the chapter your current electricity, that is dq by dt, that is known as the instantaneous current, that is I. I is equal to, in this expression, C into E0. C is the capacity, E0 that is the peak value or that is the maximum value, and both are supposed constant, and we take out of the derivative, so that the expression becomes, that is C E0 d by dt of sin omega t. Clear? And you know the derivative of sin omega t, you know that is d by d theta of sin theta, that is equal to cos theta. You know this expression, so that this expression becomes, that implies we write instantaneous current I is equal to C E0 derivative of sin omega t, we write cos omega t because your theta is there, and in place of theta your omega t is there, so that we write multiplied by cos omega t, and your omega is extra term, so that we multiplied by omega, and this is the derivative of sin omega t with respect to time, so that the expression becomes, that implies I is equal to, we write just like this, omega c multiplied by E0 multiplied by cos omega t. That implies I is equal to, in place of omega c into E0, suppose we write, in place of this we write I is 0, and what is cos omega t? Here we put the trigonometric formula, and you know the formula, that is cos theta is equal to, you know the formula, cos theta is equal to sin 90 degree plus theta, you know this formula. Clear? So that here in place of theta, here omega t is there, so that in place of cos omega t we write sin 90 degree plus omega t. That implies this expression becomes, in place of cos omega t we write, that is sin, in place of theta here omega t is there, we write omega t plus 90 degree, so that we write pi by 2, and this is the final expression of instantaneous current at any time t. Clear? At any instant of time t, this is the expression, and here in this expression one thing is there, that is I0 is equal to, we write I0 in place of omega c into E0, we write omega c into E0. This is the peak value, and here we also write, that implies I0 is equal to, we write just like this, E0 divided by 1 divided by omega c. Clear? And you know the Ohm's law, that is V is equal to IR, that implies in place of V here we write E is equal to I multiplied by R, that implies we write I is equal to E by R, you know this equation, and in place of I, that is I0, we write I0 is equal to E0 divided by R. If we compare this equation and this equation, here I0 is there, here also I0 is there, here E0, here also E0, this is the peak value, and here R for resistance, and here in place of R, 1 divided by omega c is there, that means 1 divided by omega c, that just behaves as the resistance, and this is a capacitive circuit, because a circuit only containing a capacitor, so that here 1 divided by omega C, that is known as capacitive reactance. This is known as capacitive reactance. And in place of 1 divided by omega C, we write symbol is Xc. That means finally we write capacitive reactance Xc is equal to 1 divided by omega C. This is the expression of capacitive reactance. In a capacitor circuit, capacitor AC circuit, this capacitive reactance same as resistance in case of a resistive circuit, both are same. Here resistance means that is opposition offered to the flow of current. Clear? Here also capacitive reactance means that is also opposition offered to the flow of current. AC circuit containing only capacitor. Clear? And we also discuss about capacitive reactance. And here I is equal to I0 into sin omega t plus pi by 2. And you also know the expression for EMF, that is E is equal to E0 into sin omega t. If we compare these two equations, suppose this is your equation number 1, this is your equation number 2. If we compare these two equations, in equation 1, here phase is omega t. In equation 2, this is the phase, that is omega t plus pi by 2. That means here a difference of phase is there, that is pi by 2. We also write this expression just like this, that is I is equal to I0 sin, that is omega t, in place of plus we write minus of pi by 2, same thing. Clear? That means here minus of minus pi by 2, this minus pi by 2 is the phase difference. So that we write phase difference phi is equal to minus pi by 2 radian in between EMF and current in case of a purely capacitive AC circuit. And you also know in the previous point, if the circuit containing only inductor, that means a purely inductive circuit, in that case phase difference between EMF and current, that is pi by 2, that is plus pi by 2. But in this case phase difference between EMF and current, that is minus pi by 2. Clear? That is the difference. And here that is plus pi by 2, omega t plus pi by 2. Here phase difference, here phase is omega t, here phase is omega t plus pi by 2, plus pi by 2. Plus pi by 2 means that is leads, not lags behind or ahead. That means if we compare these two equations, we write finally, if we compare these two equations, here current leads an angle of pi by 2 radian because plus pi by 2 is there. Plus pi by 2 is there. So that current leads or ahead a angle of pi by 2 radian. We write from these two equations, finally we write current leads an angle pi by 2 radian as compared to the EMF or voltage. Clear? Now you draw the phasor diagram between EMF and current. Next point, that is the phasor diagram. And here we take two axes. This one is the first axis, that is suppose y axis, and this one is your x axis. And you draw a phasor. First phasor, suppose this is the EMF phasor, and this is the origin, we write O. This point we write suppose A, that means OA vector, this is a vector. this is a vector and this is a rotating vector. You know phasor means that is a rotating vector, rotating in anti-clockwise direction, means in this direction, rotating in anti-clockwise direction with angular speed omega, that is known as the phasor. So that this is a phasor, and suppose this is the EMF phasor, and you know the equation for EMF, that is E is equal to E0 sin omega t. Here phase is omega t, so that we write phase is omega t, means this angle is omega t, and this is the EMF phasor or voltage phasor, and this is the maximum value from O to A. This is the maximum value. For maximum value or peak value, we write that is E0. And another phasor is there, that is known as the current phasor. For current, you know the equation, that is I is equal to I0 sin omega t plus pi by 2 plus pi by 2. That means current leads an angle pi by 2. Leads an angle means in the anti-clockwise direction, because the phasor rotate in the anti-clockwise direction, just like this. So that current leads an angle pi by 2. Leads means in the anti-clockwise direction, lags behind means in the clockwise direction, and here leads means we draw the phasor, that is the current phasor, that is leads an angle pi by 2. This angle, this is pi by 2, and this phasor is known as the current phasor. This is known as the current phasor, that is OB vector, and O to B, this is the maximum value, and for maximum value we write that is I0. OB means that is the magnitude. OB means that is magnitude, magnitude is I0. OB vector means that is current phasor. It is also same thing. OA means that is magnitude, magnitude is E0, that is the maximum value. OA vector means that is the phasor, that is EMF phasor. Clear? And this is the phasor diagram, because in this diagram two phasors are there. One is EMF phasor, another is a current phasor, and this is the phase difference between the two phasor, this one. Clear? Then we draw the graph between E and I. E means your EMF, or that is also known as voltage. That means a graph between voltage and current versus omega t. Now you draw the graph. Graph between voltage and current versus omega t. Same thing, here also we take two axes. This one is your EMF axis or current axis. We write that is E or I. We take voltage or current in the y axis. And we draw another axis, second axis. Suppose this one is your x axis, and in the x axis we take suppose your omega t. Omega t means that is the phase, or that is also known as the angle. And for one complete cycle, for one full cycle, that is 2 pi. Its value is equal to 2 pi. Suppose this point, this is half of the cycle, we write pi. This point, that is the full cycle, we write 2 pi. This is the initial point, we write that is 0, 0, pi, in between them we write that is pi by 2, pi and 2 pi, this is the middle point, we write that is 3 pi by 2. Clear? First we draw the graph for the EMF. Suppose this is the maximum value of the EMF. This line is the maximum value or peak value of the EMF in the positive side. And in the negative side, suppose this one is the maximum value or peak value. For maximum value of the EMF, here we write that is E0 plus E0. Here we write that is minus E0. And you know the equation? equation is equal to, that is E is equal to E0 sin omega t. Sin omega t means we write sin omega t plus 0, same thing. And here plus 0, this 0 is known as the initial phase. 0 is known as the initial phase, that means EMF starting from the point 0. So that we draw starting from point 0 at pi by 2, this is the maximum value. Here 3 pi by 2, this is the maximum value. Now I draw the graph. This is the positive half. This is the positive half. Now I draw for the negative half. Clear? This one is the negative half. And this one is the positive half of the EMF. And this is the graph. Now I draw the graph for current. Same thing. Suppose this one is the maximum value of current in the positive side, and this one is the maximum value of current in the negative side, suppose. And for maximum value of current, here we write that is plus I0, this is the peak value. Similarly, in the negative side, we write that is minus I0. And you know the equation for current, that is I is equal to I0 sin omega t plus pi by 2. That means current leads an angle pi by 2. Leads an angle means in this side. Lags behind means in the right side. Lags behind means in the right side. Leads an angle or ahead means in this side. That means ahead an angle of pi by 2 or leads an angle pi by 2. So that we draw. This is pi by 2 from this point to this point. Suppose this is pi by 2. Then you draw just starting from this point, because leads an angle pi by 2. Here this is the maximum value. So that we draw from this point. This is the maximum value. At this point value is 0. Again here this is the maximum value. At this point value is 0. Again here this is the maximum value. This is the maximum value. We draw just like this. Again here value is 0. Value of the current is 0. Clear? And this is the graph. This is blue one. This is the graph. Graph for current I. And this is red one. This is the graph for EMF E. And here a phase difference. Phase difference between EMF and current. That is this one. That is this one. This one is the pi by 2. Clear? And this is the graph. This is the graph between voltage and current versus omega t. Now what is your capacitive reactance? Capacitive reactance. And you know the expression of capacitive reactance. You know the expression of capacitive reactance, that is, you know the expression for the capacitive reactance, this one, that is XC is equal to 1 divided by omega C. This is a mathematical expression of capacitive reactance. So that we write capacitive reactance, that is XC is equal to 1 divided by omega C. XC is equal to 1 divided by omega C. And from this expression we write, that implies XC is equal to 1 divided by, what is omega? Omega, you know, that is the angular velocity. And for angular velocity, you know the equation, that is angular displacement divided by time. And for one complete rotation or for one full cycle, angle of rotation, that is 2 pi. So that angular displacement, we write that is twice pi divided by. For one complete cycle, time taken, that is known as the time period, you know that. So that in place of small t, we write that is capital T, that is equal to twice pi, that is 1 by t, that is known as the frequency. That means in place of omega, we write 2 pi f. Here in place of omega, we write twice pi f multiplied by c. This is the mathematical expression. This is the mathematical expression of capacitive reactance. This is the mathematical expression of capacitive reactance. Then what is capacitive reactance? Simply we write capacitive reactance. Capacitive reactance is the opposition offered by the capacitor to the flow of current. That means opposition offered by the capacitor to the flow of current is known as the capacitive reactance. Clear? That means when current flowing through a capacitor, the capacitor opposes the flow of the current, and that is known as the capacitive reactance. And this is the main mathematical expression. Now, if a circuit containing, or if you apply the direct current, or a battery is connected, if a battery is connected to the circuit, then what happens? And a capacitor is there. Suppose just like this, we draw a circuit. These are the external wires, and this is the first plate of the capacitor, this is the second plate of the capacitor. These are the external wires, and here a battery is connected. This one is the positive side, this one is the negative side, and here a key is also connected. This one is the key, and these are the external wires. Now suppose the circuit is now closed, and capacity of this capacitor we write C, and this is the battery, this side is positive, this side is the negative, and this one is the key, we write K, its potential difference we write, suppose that is V. That means if a battery is connected or source is DC, because from the battery, your mobile battery or laptop battery, from the battery we get the direct current, not alternating current. That means battery gives us direct current. That means if a battery is connected here, then what happens? Clear? This side is positive, this side means that is A, second plate that is B. A plate connected to the positive terminal of the battery. If A plate connected to the positive terminal of the battery, inside the plate A, because that is a conductor, free electrons are there, so that these free electrons starts to move towards the positive side of the battery. If a free electron starts to move towards the positive side of the battery, loss of electron, you know that is positive. That means first plate that is now positive charged, because loss of electron, that is positive charge. If electron starts to flow from the plate A towards the positive terminal, A plate loss of electron means that is positive charge, so that plate A gains positive charge. And at the same time, what happens? Plate B is very close to the plate A, and inside the plate B, here negative charges are there, so that in the inner side of the plate B, negative charges are induced, and in the right side, positive charges are induced, same amount of positive charges are induced. And at the same time, this side connected to the negative terminal of the battery, so that from the negative terminal, now electrons starts to flow towards the plate B, so that same amount of same number of electrons start to move, and these positive charges combine with these electrons which are flowing from the negative terminal, and both are neutralized with each other, so that finally here only negative charges are there. That means if we connect positive terminal of the battery to the A plate is positive charged. If we connect negative terminal of the battery to the B plate is negative charged. And during the charging of the capacitor, what happened? Electrons start to flow in this direction. That means this is the direction of the current. Current is there. During the charging, current flowing through the circuit. But when capacitor is fully charged, what happened? When capacitor is fully charged, total number of electron moves towards the positive terminal, that is 0. No charge particles moves in the circuit. If number of charge is 0, that means current is 0. That means after fully charged, current flowing through the circuit, that is 0. This is for DC. This is for direct current. That means after fully charged the capacitor, current flowing through the circuit, that is 0. Current flowing through the circuit is 0 means the capacitor opposes the flow of current. And you know opposition of what? That is XC. XC is equal to 1 divided by twice pi F multiplied by C. And opposition of what? That means the capacitor totally opposes. This capacitor totally opposes the flow of charge particle or flow of current. That means its capacitive reactance is equal to infinite. Capacitive reactance is infinite in case of a DC circuit, and you also know for DC same thing. For DC, frequency f is equal to 0. If frequency f is equal to 0, in place of f, if we put 0, then something divided by 0, that is infinite. So that finally we get, if a circuit containing only a capacitor and a battery is connected, that means source is DC, then during the charging, capacitor allow the flow of current, but after fully charged, the capacitor totally block the direct current. Here we write capacitor block direct current after fully charged, not before. After fully charged. Clear? Similarly, for AC, we write for AC, what happened? You know, this is the expression XC, that is the capacitive reactance, that is 1 divided by twice pi F into C. That means capacitive reactance is depend upon frequency. Capacitive reactance is depend upon frequency. If we increase the frequency of the alternating current, then capacitive reactance is decreased. That means we write, if frequency is infinite, then capacitive reactance is equal to, in place of F, if we put infinite, then Xc is equal to 0. That means capacitor allow alternating current, but that depend upon the frequency. If frequency is very small, then capacitive reactance is there. If we increase the frequency, then capacitive reactance is gradually decreased. if we draw a graph, between xc and f, suppose in the x-axis we take frequency, in the y-axis we take capacitive reactance. Here if frequency is infinite, capacitive reactance is 0, clear? And here if you increase the frequency, capacitive reactance, capacitive reactance is gradually decrease. If you increase the frequency, capacitive reactance is gradually decrease. This is the graph. That means capacitor simply control the alternating current. We write capacitor control AC, capacitor control AC, and that depend upon frequency F, clear? Simply write capacitor allow AC and that depend upon the frequency, and capacitor totally block DC after fully charged, clear? Then we will calculate the instantaneous power supplied and average power supplied. First we calculate the instantaneous value. Instantaneous power supplied to a purely capacitive AC circuit, and we know the formula. For the power. That is the electric power. That is P is equal to V into I from the chapter current electricity. So that we write instantaneous power supplied P is equal to, in place of V we write E multiplied by I. That implies P is equal to, the expression for E, that is E0 sin omega t multiplied by, the expression for current, that is I0 sin omega t plus pi by 2, this expression. That implies instantaneous power P is equal to E0, that is I0 multiplied by sin omega t. In place of sin omega t plus pi by 2, here we put the trigonometric formula, this formula, cos theta is equal to sin 90 degree plus theta, and here in place of sin 90, here pi by 2 is there, in place of theta, here omega t is there, so that is sin pi by 2 plus omega t, we write that is cos omega t. So that in place of this, simply we write cos omega t. That implies instantaneous power supplied P is equal to E0 I0, here you divided by 2 and multiplied by 2, remaining is equal to sin omega t multiplied by cos omega t. And you also know another trigonometric equation or formula, that is twice of sin theta into cos theta, that is sin 2 theta, this expression. So that in place of this we write that is instantaneous power supplied P is equal to E0 I0 divided by 2 multiplied by sin twice omega t. This is the mathematical expression of instantaneous power supplied. Then what is the average power consumed or average power supplied? Because in case of alternating circuit or AC circuit, magnitude of the EMF is gradually changed. Here magnitude is initially increased, at this point this is the maximum value. Again magnitude is gradually decreased, at this point value is 0. If magnitude of EMF or magnitude of current is gradually changed, then E and I both are not constant. That means power consumed power consumed, that is also not constant, and that is the instantaneous power consumed, or that is the power consumed at any instant of time. So that power consumed, that is a variable quantity, and in case of variable we calculate its average value. And for a full cycle, what is the average power consumed? From this expression we calculate, simply we write average power supplied, and symbol for average power supplied we write that is P bar. This bar is for the average. This is equal to, we calculate the average value, average of the right side, that is E0 I0 divided by 2 sin 2 omega t. Clear? And here in this equation, E0 I0 by 2, that is constant, because E0 is the peak value of a voltage. I0, that is the peak value of the current. So that only we calculate the average value of sin 2 omega t, because sin 2 omega t, that is not a constant, that is a variable, because this is depend upon the time. This quantity, its magnitude always depend upon the time. So that sin 2 omega t, that is variable, and here we calculate the average value of sin 2 omega t, not this one. So that we write average power P bar is equal to E0 I0 divided by 2 average of sin 2 omega t, that implies average power consumed is equal to E0 I0 divided by 2. This is the symbol for average of sin 2 omega t for a full cycle. Then what is the average value? How you will calculate the average value of sin theta or sin 2 omega t for a full cycle? Suppose in a classroom 4 students are there and mass of the 4 students are not same, then what is the average value? That means in this case mass of all the students are different, so that we will calculate the average value of mass. Suppose mass of the first student, that is M1, for second M2, for third M3, and for fourth, that is M4. So that total mass is equal to M1 plus M2 plus M3 plus M4 divided by number of the students, that is known as the average value. That means sum of all the mass divided by number of students, that is known as the average value. Here also we add all the instantaneous power. Addition means here you integrate all the instantaneous power, and all the instantaneous power means that is E0 I0 by 2 sin 2 omega t, and here only we calculate that is sin 2 omega t, only we find out the average of sin 2 omega t. So that we write that is summation of sin 2 omega t dt for full cycle. Full cycle means 0 to t divided by total time for a full cycle, you know, that is t. This is the average value of sin 2 omega t. So that in place of this we write this one. Clear? That implies average power is equal to E0 I0 divided by 2 multiplied by, in place of this we write here t is there, so that first we write 1 by t multiplied by integration from 0 to t, that is sin 2 omega t multiplied by dt. That implies average power consumed is equal to, we write E0 I0 divided by 2t multiplied by integration of sin 2 omega t dt. You know the formula for integration, that is integration of sin theta d theta is equal to minus of cos theta. You know this formula. So that we write integration of sin 2 omega t, that is minus of cos Here in place of theta, 2 omega t is there. We write 2 omega t, here 2 omega, that is extra, so that we divided by 2 omega. This is the formula. This is the formula of integration of sine 2 omega t. Integration of sine 2 omega t, that is cos 2 omega t divided by 2 omega, and its value vary from 0 to capital T. Clear? And we write finally average power consumed P bar is equal to, we take negative sign and 2 omega to the outside, so that this is minus of E0 I0 divided by 4 T omega multiplied by remaining is equal to cos 2 omega T 0 to T. That implies average power consumed is equal to minus of E0 I0 divided by 4 T omega. Here cos, what is omega? You know omega is equal to 2 pi divided by T. So that in place of omega we write twice pi divided by T multiplied by, in place of small t, first we put the upper limit. Upper limit is capital T, then minus sign. We write cos 2, in place of omega we write twice pi by T multiplied by, in place of small t we put the lower limit is 0, and this is t cancel, remaining is equal to cos 4 pi. You know value of cos 4 pi same as cos 2 pi, same as cos 0, then cos 0, its value is equal to 1 minus, here also cos 2 into 2 pi by t multiplied by 0, that is cos 0, and value of cos 0, that is also 1. 1 minus 1, that is 0, so that something multiplied by 0, finally we get average power consumed for a full cycle is 0. Average power consumed for a full cycle is 0. Clear? And the last point, that is charging and discharging of a capacitor when alternating current is there. That is charging and discharging of capacitor when alternating current is there, and for AC circuit. Clear? And you know the equation. Equation of EMF, E is equal to E0 sin omega t. This is the applied EMF. For applied voltage. And you know the equation for instantaneous current, that is I is equal to I0 sin omega t plus pi by 2. We also draw the graph of voltage and current versus omega t, this one. We also draw the graph, this one. Now we draw the same graph here. Suppose this one is the y axis and we take another axis. This one is the x axis, and in x axis we take omega t. And you draw the here graph for power, and in y axis we may take power P, we may take voltage, that is E, or we may take that is current. Clear? Suppose this is the maximum value of the power. Suppose this is the maximum value of power in the positive side, and this is the maximum value of the power in the negative side. Suppose, and here this point is the starting point, initial point, origin, we write O. Up to this, suppose this is the half cycle. For half cycle we write pi. up to this is a full cycle, we write that is 2 pi. This is the middle point between 0 and pi, we write that is pi by 2. This is the middle point between pi and 2 pi, we write that is 3 pi by 2. Clear? And suppose you write this point is 0, this point is 0, this point we write suppose 1, this point is 2, this point is 3, 4. 4 means 2 pi, 2 means pi. Clear? First we draw the graph. First we draw the graph for EMF. We draw the graph for EMF, and you know the equation of the EMF. This is the equation. This is the equation of EMF. E is equal to E0 into sin omega t. E is equal to E0 into sin omega t means this is omega t plus 0. That means EMF, its initial phase is 0. EMF is starting from point 0. Suppose this is the maximum value. Clear? And we draw the graph. This is the graph of EMF in the positive side. Similarly, in the negative side, suppose this is the maximum value. This is the graph of EMF. We write this is the graph for EMF E. Clear? Similarly, for current, you know the equation, that is I is equal to I0 into sin omega t plus pi by 2. Plus pi by 2 means leads an angle of pi by 2. Leads an angle of pi by 2 means this is pi by 2, up to this is the pi by 2. That means current, its maximum value is at this point. And at this point, value of current is 0. Again at this point, this is the maximum value of the current. Suppose this is the maximum value. Here that is 0. Again at this point, this is the maximum value of the current. Suppose this is the maximum value. Now I draw the graph. This is the graph for current. This is the graph for current. And you know this is the graph for current. We write that is the for current. And you draw the line. This is the line for 1. This is the line for 1. This is the line for 2. Similarly for 3. Similarly for 4, or for a full cycle. Now, between 0 to 1, between 0 to 1 means between phase 0 to pi by 2, what happened? We write for 0 to 1. For 0 to 1, what happened? Circuit is just like this. This one is your circuit. These are the external wires. And this one is your capacitor, and this one is your alternating EMF, this is the circuit. This is the circuit. Between 0 to 1, between 0 to 1, here EMF or voltage is gradually increased. Voltage is gradually increased. And at this point, voltage is maximum. Clear? Voltage is maximum, and here current is gradually decreased, and at this point, value of current is 0. If voltage is maximum and voltage in the positive side, voltage is in the positive side, that means to the first plate of the capacitor, we give positive, so that first plate of the capacitor now positive charged. First plate of the capacitor is now positive charged, and the second plate of the capacitor now negative charged. Clear? Between 0 to 1, the capacitor is now charged. The capacitor is now charged, so that we write this is charging of capacitor. This is charging of capacitor between 0 to 1 or between 0 to pi by 2. First plate of the capacitor is positive charged, second plate of the capacitor is negative charged, and at point 1 or pi by 2, value of EMF is maximum. Value of EMF is maximum, or value of voltage is maximum. so that capacitor is fully charged. Capacitor is fully charged at point pi by 2, and at the same point, what is the magnitude of current? Magnitude of current is 0. That means when capacitor is fully charged, the capacitor totally blocks the alternating current. When capacitor is fully charged at this point, here current is 0. This is the current. Current is gradually decreased, and at this point current is 0. That means when capacitor is fully charged, the capacitor also blocks the alternating current for a very small time, for a very fraction of time. Initially, capacitor is gradually charging. At this point, capacitor is fully charged, and here value of current is in the positive side, and EMF or voltage, that is also in the positive side. So that voltage is positive, current is positive. What is power? We write power P. You know the formula, that is voltage multiplied by current. If voltage and current both are positive, power is also positive. Power is positive. That means we draw the graph for the power. This is the graph for the power. That is in the positive side. This is the graph of power. This is the graph for power between 0 and 1. That means power is positive. That means this is the situation of charging. This is the situation of charging of capacitor. And if capacitor is now charged, then energy is observed from the source. And we write here, energy is observed from the source. Clear? Once again, between point 0 and 1, EMF is gradually increased or voltage is gradually increased, so that the capacitor is now charged, and here voltage is in the positive side, so that first plate of the capacitor is positive charged and the second plate of the capacitor is negative charged. And at point 1, this point is 1, at point 1 value of voltage is maximum, so that capacitor is fully charged. If capacitor is fully charged, that block the alternating current for a very small time. Then at the point 1, current is 0, at point 1 current is 0. And this is in the positive side, because current is situated in the positive side, its value is positive. Voltage is also situated in the positive side between point 0 and 1, so that both current and voltage both are positive, so that power is positive. Power positive means we write energy is observed from the source. Clear? Then between point 1 and 2, we write between point 1 and 2, what happened? Between point 1 and 2, look at the figure. EMF, its value is now gradually decreased, or voltage is gradually decreased, its magnitude is gradually decreased between point 1 and 2. And current is now reversed. Current is now negative, but voltage is gradually decreased. If voltage is gradually decreased, current its direction is reversed, that is negative. Now the capacitor is discharged from point 1 to 2, capacitor is gradually discharged, and at point 2 capacitor is fully discharged, so that between point 1 and 2 now the capacitor is gradually discharged, just like this. Clear? If capacitor is gradually discharged, then if capacitor is gradually discharged, what is the power? We write here power P. P is equal to same thing, E multiplied by I. Here E or voltage is positive, that is in the positive side, because this side is positive, this side is negative, current is negative, so that positive multiplied by negative, that is negative. Power is in the negative side, so that we draw the graph for the power. This is the graph for the power between 1 and 2. Between point 1 and 2, this is the graph of power. Power is in the negative side. If power is negative, then we write the energy is returned back to the source. The energy is returned back to the source. Clear? That means once again, between point 1 and 2, voltage is gradually decreased, so that the capacitor is now discharged, starts to discharge. Then at the same time, magnitude of current is gradually increased, but in the negative side, so that voltage is positive, current is negative. That means power is negative. Power negative means energy is returned back to the source. Then between point 2 and 3, we write between point 2 and 3, what happened? Between point 2 and 3, now voltage is in the negative side. That means a negative voltage is applied. If a negative voltage is applied, first plate of the capacitor is now negative charged. First plate of the capacitor is now charged with negative, and second plate is now positive charged. Clear? Between point 2 and 3, now once again the capacitor is now charging, and at this point your magnitude of the voltage is maximum, so that once again capacitor is fully charged. Once again capacitor is fully charged at point 3 pi by 2. Clear? And at this point, at point 3 pi by 2, look at the graph. This is the graph for current. Current is 0. That means if capacitor is fully charged, current is 0. That means once again capacitor block alternating current for a very small time. That means between point 2 and 3. Between point 2 and 3, what's about your power? You know the formula for power. Power is equal to E into I. Here E means voltage is in the negative side. Current is also in the negative side. Both are in the negative side. Negative into negative, so that finally we write positive. That means power is positive. Power is positive means simply write energy. We write energy is observed from the source. Clear? And here once again, between point 2 and 3, voltage is magnitude is gradually increased, but in the negative side, so that first plate of the capacitor is now charged with negative, and the second plate is positive. And at point 3 pi by 2, magnitude of the voltage, that is maximum, so that the capacitor is fully charged. And at point 3 by 2, magnitude of the current is gradually decreased, and that is 0, so that capacitor totally blocks alternating current for a very small time, and your power is positive, so that energy is observed from the source. And the last point, between point 3 and 4, we write between point 3 and 4. Between point 3 and 4, what happened? Between point 3 and 4, that means 3 pi by 2 to 2 pi. Here magnitude of the current is gradually increased, and magnitude of the voltage is gradually decreased. If magnitude of the voltage is gradually decreased, then the capacitor starts to discharge, so that once again the capacitor is now discharged. Once again the capacitor is now discharged, just like this. Clear? Then here voltage is in the negative side. Current is in the positive side, so that power P is equal to negative multiplied by positive, that is negative. If voltage is if power is negative, then the graph is just like this. Between point pi to 3 pi by 2, power is positive, so that we draw the graph. Between point 3 to 4, power is negative. Power is negative means power is situated in the negative side. And this is the graph for power. Clear? That means between point 0 and 1, capacitor is not charging. Between point 1 and 2, that is the discharging. Again between 2 and 3, once again charging. Between 3 to 4, once again discharging. Clear? And this is all about your AC circuit containing capacitor only, or a purely capacitive AC circuit. And in the next class, we will discuss about series LCR circuit and impedance. And thank you.